Now that we discussed aldol condensation reactions in combination and we discussed what Magid's second rule is, let's take a look at the following example that is basically a reaction in which we have our aldol condensation in combination taking place. So this is another application in which we're going to use Magid's second rule. So let's begin by looking at our reaction. So we basically want to determine what the reaction mechanism is when we go from these two carbonyl compounds, our aldehyde and ketone, to this particular product. So we're mixing in our base catalyzed condition. So we have a base in the presence of water. Now, what exactly is the first step? Well, the first step in this reaction is basically the deprotonation of an alpha carbon, of an alpha hydrogen from our alpha carbon found on either this or this carbonyl. The question is, which one will be protonated first? Now, basically, we want to apply Magid's second rule. And Magid's second rule tells us that the first reaction that we have to try in the aldol combination reaction is the one that takes us through Michael reaction. And the Michael reaction basically is a reaction between a nucleophile and an alpha beta carbonyl, an alpha beta unsaturated carbonyl. So that basically tells us that the first thing that we're going to try is we're going to try to deprotonate this alpha H atom of this alpha carbon, and then that nucleophile will attack this molecule via the Michael reaction. So according to Magid's first rule, or Magid's second rule, I should say, that tells us that the Michael reaction takes place first. So that basically means this base that we have in our mixture will react with this molecule to deprotonate the hydrogen that is found on the alpha H. And the alpha H is basically this H atom here. So we have this molecule which has a negative charge, deprotonates this H atom, placing our electrons onto this carbon here. And we form the following intermediate that is resonance stabilized. And this intermediate will basically act as our nucleophile in our reaction. So we have these two electrons here. We have our carbon-oxygen double bond, and we have resonance stabilization. So we have a negative charge here, but these electrons can go onto here, kicking off these electrons, placing them onto our oxygen, and we can also form the second resonance stabilized form, which basically looks something like this. So we have our oxygen that has a negative charge, and we have our H. And the negative charge in this case is delocalized onto the oxygen. Now, in the process, we also form our water molecule that will play a role in the next several steps. So this is the formation of our enolate or enolate. This is our enolate that is formed, and now the enolate will act as a nucleophile via the Michael reaction. So the next few steps involve the Michael reaction, including this step here. So in the Michael reaction, we basically have our nucleophile, this molecule, basically reacts and binds to the beta carbon of our alpha beta unsaturated carbonyl. So that's this molecule right here. So basically these two electrons here attack this carbon here, the beta position carbon, displacing these electrons, placing them onto the alpha carbon, and we form the following molecule. So we basically have the following structure that is formed. So let's do our best to draw. So we have our here, and we have